Good morning, my dear students. We are on another session of online classes. Today, we have to continue our discussion regarding the structure of glucose. In the previous class, we have discussed the first part of structure of glucose, that is the open chain structure of glucose. Now, we have to discuss about the second part of structure of glucose, that is the configuration of glucose. Configuration of glucose. To find out the configuration of glucose, we have to take D-arabinose as the standard, because for D-glucose and D-arabinose there is some similarity in configuration. So if I consider this is arabinose, the configuration of the second carbon atom, third carbon atom, fourth carbon atom and fifth carbon atom of D-arabinose, that is the configuration of the last four carbon atoms of arabinose, are exactly same that of the last four carbon atom of glucose. And we know glucose is a hexose sugar, contains 6 carbon atom, while arabinose is a pentose sugar. So when I consider D-glucose and arabinose, the configuration of the last four carbon atoms for glucose and arabinose are same. And we know for both glucose and arabinose, the first carbon atom is an aldehyde group. That means we have to only find out the configuration of the second carbon atom present in glucose, because glucose is a aldohexose, that means it contains 6 carbon atom, and the configuration of last four carbon atoms are same as that of D-arabinose. Okay, take down. To confirm the configuration of the second carbon atom of glucose, we have to subject arabinose to Killiani-Fischer synthesis. Killiani-Fischer synthesis is the process by which a lower aldose is converted to a higher aldose. That means if I carry out Killiani-Fischer synthesis to arabinose, arabinose is a 5-membered aldopentose. It undergoes Killiani-Fischer synthesis to form aldohexose. That means monosaccharides contains 6 carbon atom. So when I carry out Killiani-Fischer synthesis, always I will get epimers as the product. And we know epimers or isomers have only difference in configuration for one asymmetric carbon atom or one chiral center. So to find out the configuration of the second carbon atom of glucose, I am subjecting arabinose to Killiani-Fischer synthesis. See here, this is arabinose. So for this arabinose, the last four carbon atom, the configuration of last four carbon atom are exactly same for these two products, that is the Killiani-Fischer synthesis product 1 and 2. The only difference between 1 and 2 is the configuration for the second carbon atom. For the first structure, the OH group is on the right hand side, while for the structure 2 the OH group is on the left hand side. Hence these two structures 1 and 2 are epimers. So when we carry out arabinose to Kiliani-Fischer synthesis, I will get two aldohexoses. Out of these two aldohexoses, one is glucose. Now we have to find out whether first one is glucose or second one is glucose. If we identify first one as glucose, then this is the configuration. If second one is glucose, this is the configuration. That means for structure 1 and structure 2, only the configuration difference is for the second carbon atom. So now we have to identify which is glucose, first one or second one. Take down. To confirm the configuration of glucose, we are subjecting the structure 1 and 2 obtained from arabinose to further Kiliani-Fischer synthesis. And we have the doubt which is the glucose structure, whether it is structure 1 or structure 2. So we take both the structures 1 and 2. One is glucose or 2 is glucose, that we don't know. One is mannose or 2 is mannose, that we do not know. So we take structure 1 and structure 2 and further subjected to Kiliani-Fischer synthesis. When I carry out Kiliani-Fischer synthesis, I get two epimers of aldoheptoses because the structure 1 and 2 contain 6 carbon atoms. Structure 1 will give you 2 epimers aldoheptoses. Similarly, structure 2 will give you 2 aldoheptoses. That means aldose with 7 carbon atom. Now, the aldoheptoses obtained from mannose, we have experimentally proved that the aldoheptoses obtained from mannose on oxidation with the concentrated nitric acid give 2-dicarboxylic acid, which are optically active. So if structure 1 is mannose, the aldoheptoses obtained from structure 1 on oxidation with nitric acid gives 2-dicarboxylic acid, which are optically active. Now, if the aldoheptoses obtained from glucose, they are subjected to oxidation, will give you two isomers. One is optically active and another is a meso compound. So, we take the aldoheptoses, we subject them to oxidation and we study which is optically active and meso compound. From this identification, we could confirm the structure of glucose molecule. Take down the point before moving to next slide. Now we take structure 1 and subjecting to Killiani-Fisher synthesis. And we know structure 1 and 2 contain 6 carbon atoms, which on Killiani-Fisher synthesis gives you 2 epimers each having 7 carbon atom, that is aldoheptosis. See, we are going to carry out Killiani-Fisher synthesis to structure 1. Now, this is structure 1 having 6 carbon atom. 1, 2, 3, 4, 5, 6. This may be glucose or this may be mannose. So, if it is glucose, this is the configuration. So, we have to confirm whether this is glucose or mannose. So, I am subjecting glucose to Killiani-Fisher synthesis so that I will get 2 epimers. See the configuration for glucose and these two CH2OH. Then from bottom second carbon atom, OH group on the right hand side. Here also OH group right hand side. Here also OH group right hand side. For this third carbon atom, OH on the right hand side. Here also OH on the right hand side. Moving to this carbon atom, that is the third carbon atom. So here also H on the right hand side. Here H on the right hand side. Here also H on the right hand side. Moving to the second carbon atom, OH on the right hand side. Here also OH on the right hand side, OH on the right hand side. Now, after Killiani-Fisher synthesis, a new carbon atom has come. One here, one here. In this molecule, the OH group is on the right hand side. And this is the epimer in which OH group is on the left hand side. See, apart from this carbon atom, all the configuration are same. Hence, these are epimers. Now, we have to see. See, I am subjecting this molecule to oxidation. These two molecules to oxidation. And when I oxidize, this COH group will be converted to COOH group. And CH2OH group will be converted to COOH group. That means here one COH, here one COH. Similarly, here also one COH and here one COH. That means 2 dicarboxylic acid, because here one COH, here another COH. So 2 carboxylic group. Hence it is a dicarboxylic acid. Now I am taking the optical activity. See, the aldoheptosis obtained from glucose on oxidation with concentrated nitric acid gives 2 dicarboxylic acids. One is optically active and another is meso. Now see here, we know for any compound to show optical activity, the compound should not have any symmetry elements. Okay, so now see here, I am taking this molecule, 7 carbon atom. This is the plane of symmetry. This is the plane of symmetry. This plane of symmetry. This carbon atom acts as the plane of symmetry. I am looking back down to this carbon atom. 1 OH, 2 OH group. Here top 2 OH group. That means this is a meso compound because this is having a plane of symmetry, a line of symmetry. Hence, this part is same as of this part. Hence, this is a meso compound. Now move to the second one. See here, taking this as the line of symmetry. Line of symmetry. This part is not equal to this part. That means this molecule does not have any symmetry. Hence, this is optically active. So, experiment says that the aldoheptosis obtained from glucose on oxidation with the concentrated nitric acid give 2 dicarboxylic acid. One is optically active and another is meso compound. Now, this is a meso compound and while this is optically active. Hence, we can say this structure 1 is the configuration of glucose and this is glucose molecule. So, we can say structure on is glucose molecule. Okay, take down carefully. Then I will go to next slide. Now we take the second structure that obtained from the arabinose and we will check whether it is glucose or mannose. So this is the second structure which is obtained from arabinose. So we have to check whether this is glucose. So 6 carbon atoms are there which is subject to Kiliani-Fisher synthesis, so that I am getting 7 carbon atom aldoheptoses. So I will get 2 aldoheptoses. Only for these two there is difference in configuration for this carbon atom, that is the second carbon atom. Hence these two are epimers. See here, this is CH2H, here also CH2H. The configuration of this carbon atom is same. This is same. This carbon atom is same. Only the configuration is different for second carbon atom for these aldoheptoses. Now we know the aldoheptoses obtained from mannose on oxidation with concentrated nitric acid gives 2 dicarboxylic acid. See, this CHO group is converted to COH group, here also COH group. Similarly, here also COH group and here also it is COH group. So these 2 dicarboxylic acids I am taking, and we have to check about the optical activity. I told you, for any compound to exhibit optical activity, there should not be any symmetry elements. Now see here, this is the central carbon atom. This is the line or plane I can draw. When I draw this plane, this half is entirely different from this half. That means here 2 OH group on the right hand side, here only 1 OH group and 1 H group. That means this molecule does not have any symmetry elements. Now we check the second molecule. Same thing. This is the central carbon atom. If I draw a line here, it is a line of symmetry. But when I am looking here, this molecule 2 OH group on the right hand side, here 2 OH group on the left hand side. That means these two molecules does not have any symmetry. Hence these two are optically active. So this structure 2 is not glucose, it is mannose. So we have confirmed this is not glucose, this is mannose, and the structure 1 was glucose. Take down. So the configuration of glucose is shown here and that of mannose shown here. First carbon atom is CHO for both. Second carbon atom for glucose OH on the right hand side, while for mannose OH on the left hand side. For glucose, for third carbon atom H on the right hand side, mannose also H on the right hand side. For glucose, fourth carbon atom OH, fifth carbon atom OH on the right hand side. For mannose also same configuration. So this is the configuration of glucose and this is glucose molecule identified. And this is mannose, which is the epimer of glucose, having a difference in configuration only at the second carbon atom. So be careful, this is the structure of glucose. When you write from bottom CH2OH, 2 OH group on the right hand side, 1 H group on the right hand side and 1 OH group on the right hand side. So we have seen the first two parts on the structure of glucose, that is the open chain structure and the configuration of glucose. But many properties of glucose were not able to be explained using the open chain structure. And in polysaccharides and oligosaccharides, the structure of glucose is not as an open chain structure. Hence, we are moving to the third part, that is the ring or cyclic structure of glucose. So, moving to the cyclic structure of glucose, here the reactions has to be observed. The open chain structure of glucose cannot explain why glucose does not form an addition product with hydrogen sulfide. That means glucose does not react with sodium bisulfite to form hydrogen sulfate addition product. The second thing is that even though glucose have a aldehyde, it does not give the Schiff test. And we know Schiff test is the confirmatory test for aldehyde, but glucose does not answer Schiff test. Open chain structure was not able to explain about the existence of two isomers alpha and beta D glucose that we have seen in mutarotation. Finally, this open chain structure was not able to explain about the phenomenon of mutarotation. So, a cyclic structure was proposed by connecting the aldehyde group, that is the first carbon atom, with the fifth carbon atom. See here, this is the aldehyde group. The lone pair of electron from the fifth carbon atom attacks this particular carbon. As a result, this O will get a minus sign and this H will come and attack here. So we will have a cyclic structure. That is, we are connecting the first carbon atom with the fifth carbon atom to form a cyclic structure as we have seen in mutarotation. Take down. When we discussed mutarotation, we had seen the formation of anomeric carbon atom and the two isomers alpha and beta D glucose. Once again, we are seeing same thing. This is the open chain structure and this carbon atom gets combined with the fifth carbon atom, resulting the formation of a cyclic structure. So, see the configuration. This is the open chain configuration of glucose and the configuration of these carbon atoms are not changing, but the first carbon atom become asymmetric. If the OH group is on the right hand side, it is alpha D glucose, and if OH group is on the left hand side, it is beta D glucose. See, the configuration of these carbon atoms remain as such. So this is the cyclic formation of glucose molecule. Take down. Haworth, a scientist, he converted or represented or correlated the cyclic structure of glucose that we have seen with a heterocyclic molecule, and it is called the Haworth representation. He correlated the cyclic structure of glucose with a heterocyclic molecule called pyrran, and the glucose structure is modified to the form of pyrran structure. See here, when the glucose molecule is correlated with the pyrran molecule. See, this is the heterocyclic molecule called pyrran. So there is an oxygen linkage. See here, first carbon atom, second carbon atom, third, fourth, fifth carbon atom. 5 carbon atoms are there in this particular molecule. And the first carbon atom and fifth carbon atom are connected with an oxygen atom or oxygen. See this structure, we are correlating this to Pirano structure. Now see here, when I consider this glucose molecule, I have first carbon atom, second, third, fourth, fifth and sixth. The fifth carbon atom is connected through an oxygen to the first carbon atom. So when I represent this molecule to Pirano structure, the atoms or group of atoms present on the right hand side, OH, OH, H and OH, are at the bottom position of this particular ring, while the H, OH, H and H, these are the atoms or group of atoms present on the left hand side. They come above the plane of this particular ring. So I am taking pyrran molecule and I am converting to a pyrrano structure, and it is correlating with the cyclic structure of glucose. So during that particular correlation, this ring is in a particular plane, and the first carbon atom is connected with fifth carbon atom through an oxygen atom, and hence the group or atoms coming on the right hand side should be placed below the plane of this ring, and the group of atoms coming on the left hand side should come above the plane of the ring. I repeat, the atoms or group of atoms which are coming on the right hand side, right groups on the carbon atom, go to the bottom position of the ring. This is the Haworth ring, while these groups or atoms present on the left hand side should go above this particular ring. That representation is Haworth representation, and we are going to see it in the next slide. Take down. Okay. You ready? Now see here, we are moving to how alpha D glucose and beta D glucose are converted to pyranose structure. So we have to see how they are correlated to the pyranose structure. See here, this is the corresponding open chain structure of glucose. So the fifth carbon atom, that is the OH group, combines with the carbon atom, this carbon atom, resulting the formation of a cyclic molecule. So this first and fifth carbon atoms are connecting through the oxygen linkage to form the molecule. See here, the first carbon atom is connected with the fifth carbon atom through an oxygen linkage. Now this structure we are converting to pyranose structure, that is alpha D glucopyranose and beta D glucopyranose. See here, this is alpha D glucopyranose. See here, this is alpha D glucose. So the OH group, this is the anomeric carbon atom. First carbon atom connected with the fifth. See, this is the first carbon atom connected with the fifth through an oxygen atom. Now the first carbon atom configuration OH on the right hand side. So the OH should come below the plane for the first carbon atom. H on the left hand side, it placed above the plane of the ring. Now I am taking second carbon atom. The OH group is on the right hand side. See, second carbon atom. OH group is on below the plane. H on the left hand side. See, above the plane. Similarly for 3, H on the right hand side and OH on the left hand side. So H down to the plane or below the plane while OH above the plane. Moving to the fourth carbon atom. The OH group is on the right hand side, H on the left hand side. See, fourth carbon atom. OH below the plane and H above the plane. Now moving to the fifth carbon atom. Fifth carbon atom is having hydrogen on hydrogen and one CH2OH group. This is a bulky group. So we may think this is H which is placed in the left hand side, so it should come above the plane. But this is a bulky group. So we place CH2OH above the plane and H below the plane for the fifth carbon atom. This is alpha D glucopyranose. Why? Because this is glucose, alpha D glucose, OH group is on the right hand side. So converting to alpha D glucopyranose, in the anomeric carbon atom, the OH group is on the bottom of the ring plane. Now see, this is beta. We know when it is a beta D glucose, this OH group should be on the left hand side. H should be on the right hand side. All the other configuration remains same. So between alpha D glucose and beta D glucose, that is alpha D glucopyranose and beta D glucopyranose, only difference is the anomeric carbon atom. Here the OH group is below the plane of the ring, while here OH group is above the plane of the ring. All other configuration is same. There is no change. So like alpha D glucose and beta D glucose, we have alpha D glucopyranose. Why it is pyranose? Because alpha D glucose is correlated with the pyran molecule to have alpha D glucopyranose. Similarly, we have beta D glucopyranose. So this is the structure of alpha D glucopyranose and beta D glucopyranose. Only change in configuration or placement of H and OH group for the first carbon atom. If it is alpha, OH group is down to the plane. If it is beta, OH group is above the plane. Okay? Clear? Take down, very important. So we have seen alpha D glucopyranose and beta D glucopyranose structure. Both alpha D glucopyranose and beta D glucopyranose are hexagonal structure. Hence, it could be represented in the form of chair and boat conformation. We have seen for cyclohexane, two conformations are possible, extreme conformations are possible, boat conformation and chair conformation. Similarly, alpha D glucopyranose and beta D glucopyranose are cyclic hexagonal ring. So we are converting them to chair conformation and boat conformation. And see here, this is Haworth presentation. This is beta D glucose because OH group is above the plane. And we have the chair conformation here. See here. And we have the boat conformation here. These two conformations are possible. But we know chair conformation is more stable than boat conformation. Because here first and fourth carbon atom repulsion is there. Here first and fourth is at maximum distance. So repulsion is minimum. Hence chair conformation is more stable than boat conformation. Okay, take down. See, now we have to represent the chair conformation of alpha and beta D glucose because we know chair conformation is more stable than boat conformation. So we are going to represent the chair conformation and boat conformation of alpha D glucopyranose. Glucopyranose. Now see here, this is alpha D glucopyranose, that is the chair conformation of alpha D glucopyranose, and this is the chair conformation of beta D glucopyranose. See, this is the anomeric carbon atom. This is the first carbon atom and this is the fifth carbon atom. Fifth carbon atom is having a H group and a CH2. This is CH2 group, CH2OH group. And fifth and first is connected through oxygen atom, Similarly here, this is the first carbon atom and this is the fifth carbon atom connected through oxygen. See, in case of alpha D glucose, this OH group is the axial bond. Why it is axial bond? Because this is the axis. We are taking this is the axis of this molecule. This is parallel to the axis. So here the OH group is the axial bond while H is the equatorial bond. So in alpha D glucose, the anomeric carbon atom having OH group as axial bond, while in beta D glucose, the OH group is the equatorial bond. So equatorial bond is perpendicular to the axis. So OH is the equatorial bond. So the difference between alpha and beta D glucopyranose in chair conformation is that in alpha D glucopyranose, OH group is in the axial position for anomeric carbon atom, while for beta D glucopyranose, the OH group is in the equatorial position. Remaining carbon atom, there is no configuration change. All configurations are same. Only configuration change is to this anomeric carbon atom. Take down. So go through the topic once again, check and confirm the structures and study properly. Study the configuration of glucose and the different structures of glucose, that is alpha D glucopyranose, beta D glucopyranose and its conformations. Anyway, thank you. Thank you for another session. We meet again on next Thursday. Till then, keep safe, be at home, and see you. Thank you. Thank you very much.